We'll provide a quick introduction to the web application we are going to deploy. Then we will create a Kubernetes cluster on Google Container Engine. We then deploy containers. We deploy our containers using replication controllers. We then test the replication controllers. After that, we deploy a few services, and then finally we test the services. So this is the cluster we are going to be deploying. And the cluster is simply a web application that has 3 front-end instances. Each one of them is a simple web app that runs on a Jetty servlet container. The front-end tier talks to a back-end tier, and the back-end tier contains 2 simple HTTP servers that invoke the Gravis process. Now, this is a non-containerized version of the web app we are going to be deploying. So the user simply puts in their graph, textual representation of the graph. They click run the graph. That goes to the web server using Ajax, and then the web server invokes the backend server to run the graph as SVG, and then the graph is displayed back to the user. We have a load balancer balancing traffic from the internet. So we have 3 replicas of the same web app or the same container. Then we have a load balancer that load balances between 2 replicas of the backend servers. There's no persistence in this example. The end game and what we hope to achieve is to have something like this deployed on Google Container Engine, and I'll briefly explain the key components in this diagram. So when we deploy our cluster, we will have some compute engine nodes or compute engine VMs that have the Kubernetes platform installed. We will have a Kubernetes master. The master is managed by Google Container Engine. And also we have a repository of images, which could be the Google Container Registry or the public Docker registry. Our containers will be deployed in pods, and they will be deployed to each one of the nodes. And we will also have replication controllers and services. So let's start off by deploying the cluster. First of all, we need to create a new project. So we head over to the Google Cloud Console and we type in the project name. After that, we hit the create button. Okay, the project is now created. So we click on the project. And if we go to the gallery and simply visit Compute Engine just to activate the APIs. So as you can see, Compute Engine is getting ready. And we can do the same for Container Engine as well. Okay, now we click on this icon to activate the Google Cloud Shell. The Google Cloud Shell is simply a terminal on a VM, temporary VM. And all the data we save in our current directory, which is a home directory, is persisted. Any other data you change in a VM will be lost once this shell is finished. So first thing we do is we choose the compute zone. And we are going to go for the US Central 1A. So G cloud config. Okay, once we've done that, now it's time to create the cluster. And you can create the cluster using this command, gcloud container clusters create Gravis app. That's the name of our cluster. If we do not specify the number of nodes in a cluster or the type of VM to use, Container Engine by default will create 3 nodes, 3 VMs, and their type will be N1 standard 1. So a machine with 1 CPU core and 3.75 gigabyte of RAM. So we hit enter. Okay, the cluster is now created. As you can see, the command has finished successfully, and it gave us some details as to the zone where the cluster is created, the name. This is the Kubernetes version. This is the Kubernetes master IP address, machine type, and the number of nodes and the status of the cluster. So effectively, what we have done is we have created this cluster. We've created 3 Compute Engine VMs, all pre-set up with the Kubernetes platform. And we also have a Kubernetes master, which is managed by Container Engine. So if we go over to the Cloud Console and just verify that actually these are just normal Compute Engine VMs, if you go to the gallery and then click on Compute Engine, you can see we've got 3 nodes, so we can SSH into them. And if you go over to the networking tab, you can also see there are some routes being set up for the cluster and some firewall rules as well. So it's all pretty much set up for us. We don't have to do anything. It's a fully running cluster that we can simply use to deploy our pods. Okay, so now if we go back to the Cloud Shell, let's just clear this one. The next step is for us to describe this cluster. So you can simply just type gcloud container clusters describe and the name of our cluster. This will show many details, creation time, versions of Kubernetes installed, security certificates for the master or for the cluster, and in here you've got a password and a username, and these are actually the username and password for the Kubernetes UI, which we will see shortly. So now, so far, we've been interacting with this cluster using the Cloud SDK gcloud command. It's about time now we start talking to the cluster using the Kubernetes or the kubectl command. So if we type kubectl cluster info, that gives us some URLs and IP numbers. So the Kubernetes master is running at this address, and then some other details, kubedns and the kubeUI. We're interested in this kubeUI, so I'll copy the URL. Then if we start a new tab, and there you go. This is the kubeUI, which is just a user interface running on the Kubernetes master. Gives a view. I've got a chart here showing the status of the 3 nodes in terms of memory usage, disk usage, and CPU utilization. There are other views as well, so you can explore pods, nodes, replication controllers, services. You might be asking yourself, how is the kubectl command able to find this cluster? And this is the beauty of the Google Cloud SDK, is that it will pretty much pre-configure things for you, so you don't have to really provide any details for the kubectl command. The kubectl expects a directory, .kube directory, so if I cd into that directory, you can see it's there, and I've got a config file which is basically used by the command to determine which clusters I've got pre-configured and their authentication details. Next step is to deploy our application controllers. The cluster configuration files are in GitHub. They're basically 4 files. So backend controller, backend service, front-end controller, and front-end service. We will start off by deploying both the backend controller and the front-end controller. But first of all, we need to check out this project into our Google Cloud Shell. So if we head back to the Cloud Shell, okay, so now we will be deploying the backend controller first. Okay, before we deploy our application controllers, we edit the configuration files to get them to point to the public image in a Docker centered registry, because the images I've got here are my private images on the Google Container Registry in a different project. We can, for example, build these images and deploy them to the container registry on this project, but that will take a while. So for the purpose of this video, I'll just simply use my public images on the Docker central registry. So if we uncomment this and then comment this line, save the file, do the same for the front-end controller. Okay, so now we're all done. It's time to deploy our backend controllers. So to deploy the backend controllers, you simply use the kubectl command and create, and then the -f flag, and give it the backend controller configuration file name, and it said it's created. So what we can do to verify that is created is we can use the kubectl command again. We say get replication controllers rc, and that gives us details. It says we have 2 replicas, this is the selectors. So now let's check the pods deployed as a result of this command. So our file for the backend controller has 2 replicas, and this is the pod template. So the pod template is simply deploying the Gravis server. So we expect to see 2 pods created. Now if we quickly go back to the Cloud Shell and simply just type kubectl get pods and pass the -o flag to show more details, and that simply says we've got 2 backend pods and these are the nodes they're running on. Again, if you head over to the Kube UI, the Kubernetes UI, you can see there's some activity in terms of memory and previous CPU utilization, and I can just guess that the 2 pods are actually deployed into this node and this node, because the memory utilization is more. CPU history seems like they had 100% CPU utilization a while ago, while this node seems to be quiet and memory utilization as it was before. So now I can also view the status of these pods. If I click here, you can see we've got 2 of them and they're running, and this is the images they're based on. If we view the replication controllers, again I've got 1 replication controller, which is the one I just deployed. So if we head back here, these are compute engine VMs, so technically we can SSH into one of them and just double check that actually yes, we've got these pods deployed. So what I'll do is I'll SSH into, say, this VM, this node, and then just simply run the docker ps command on it. So okay, we're there. So now sudo docker ps. Okay, we've got a few images running. Some of them are actually to do with the Kubernetes platform itself, so we're not really at this stage we're not really concerned about them. But this is our Gravis server container. It's been deployed, is up 3 minutes. Next step, if we exit from that one, okay, we deploy the front end controller again by using the kubectl create, and then we pass in the file name for the front end controller. Okay, and that's being created. So we just double check the kubui just to see. As you can see, there's some nice activity here. So CPU utilization of the nodes, memory utilization. Okay, because we are deploying 3 pods, then there will be a pod on each node. So this node will have 2 pods, one front end, one back end. This node has 2 pods, one front end, one back end again. This node has 1 pod, which is a front end pod. At this stage, the cluster should look something like this. We have the 3 nodes, and we have 3 front end pods, which are the green ones, and they labeled with green label, and they are monitored by a front end controller. At the same time, we've got 2 backend pods with the blue labels, and they are monitored by a backend controller. This is the current state of the cluster. So now if we head to the kubui and just verify that we're actually now got 5 pods, 3 front end and 2 back end. As you can see, there's 5 of them. If we head over to replication controllers, we should have 2 now. So we've got 2, we've got a back end controller, we've got a front end controller. And if we head back to the Cloud Shell, just to double check, so if we type kubectl get rc, show the replication controllers, as you can see we've got 2 of them. The backend controller is responsible for 2 replicas, and the front end controller is responsible for 3 replicas. Let's also get the pods. Okay, 5 pods, all running already, 2 backend and 3 front end. So next step, we want to test the replication controllers. So the purpose of the replication controllers is that they always ensure that the number of replicas we specified are up and running. If one pod dies or one container dies, it will get replaced so that the number stays the same. If, however, you have more pods than you need, the replication controller will shut down some of the pods, so the number is always the number of replicas. It's a cool feature. You can use it for rolling updates. You can use it to scale up your pods if you have more nodes. So in this stage, we will test this feature by purposely going in and killing one of the containers, just to double check that actually the replication controller will replace it. Okay, so if we head back, we're just gonna SSH in any of the nodes. Basically, the front end pods are deployed to all the 3 nodes, so it doesn't matter which one we SSH into. It will have a front-end pod. So now if I SSH into, say, this one, okay, so now we're in there. So let's list all the running Docker containers. Sudo docker ps. Okay, I've got a few of them running. Basically, this is my front end container. Simply copy the container ID. What I'm going to do, just bear with me, it's been running for 5 minutes. So what we're going to do is we are going to kill it. And we do this by doing sudo docker kill. Okay, container's dead. Okay, so by now we're hoping that the replication controller has replaced or restarted this pod. So if we verify that and we do sudo, voila, you can see that the container has already been replaced, basically. So this one is up 46 seconds. Now, if we exit and just double check using the kubectl command, get pods, you can clearly see that this front end pod that we just killed is actually being restarted once. So there you go. This is how the replication controller works. It monitors these pods, and if one dies, it brings it up. If we have more pods running than what we need, simply kills a few. You can actually scale your pods by simply using the kubectl command. So you can do, if you want to scale it up to 5, we can just do ctl is scale application controllers and the name of our controller, and tell it that we want 5 replicas. By doing this, you'll simply scale up your pods. So the next stage, we want to deploy our services. Basically services, because now we've got 3 front-end pods and we've got 2 back-end pods. There's actually no connection between them. We want a way to be able to transparently say, I want to refer to a front-end pod, or I want to refer to a back-end pod, without having to know IP addresses, because as we've seen, pods come and go, they can die, they can come back with a different IP address. So IP addresses, to statically refer to them using IP addresses is not reliable. We need a way to be able to dynamically resolve to a particular pod, and this is where services come in. So if we head back to the Cloud Console, we have deployed our backend controller and front-end controller. So now we will deploy our backend service, which simply will provide a transparent way of load balancing between our 2 backend pods. So these 2 pods will create a service that will provide transparent load balancing between them, and we'll simply be able to refer to them by using this name, the backend service, and the service will do DNS name resolution to one of the pods. Okay, so we deploy the backend service. Okay, that's been created successfully. Just verify that it's actually running, get services. There we have it. We've got the backend service. Just worth noting that this service is running on port 80, that is targeting port 8080 on the host, which is the port on which our Gravis server is running. There are 2 verifications we need to do here. First of all, we need to verify this service We need to verify that this service is actually facilitating DNS name resolution. So the service we've created is called backend service. Okay, backend service. This is the name. And this name is actually used by the front end web app. So in our servlet in the front end, it's simply referring to backend service like this. So it's using HTTP backend service. So we will expect the service, the backend service, to at least resolve this reliably into an IP address that we can actually use. We don't really care, the IP address will change, but our application can reliably just reference a host name or a service name that will later on be resolved to an IP address. Let's SSH to any of the nodes, because we know all of them will actually be running the front end pods. Okay, once we're in there, we do sudo. Okay, note the container ID of one of our front end pod. I use the name pod or container interchangeably. Basically, if you deploy one container, Kubernetes will deploy it in a pod. So a pod can contain more than one containers, but I'll simply be using pod or container to just refer to the same thing. What we'll do now is we will start a shell on this container. This is one of our front end containers. It's running the Jetty server with our web application deployed. And in our web application, we have a servlet that uses backend service as the host name. And that needs to resolve to an IP address. And we just want to verify that actually this backend service will be resolved to an IP address by logging into the container, starting a shell on the container, and then doing an NS lookup for backend service just to make sure it will actually resolve to an IP address. So now if I start a shell on this container, and the container ID, which we just copied, and start bash shell. Okay, so we win. So if I do ns lookup, it's not found because I haven't got it installed on this particular image, but we can just get it using apt-get. We're simply doing this just to really verify. We don't need ns lookup on that container. I'm just doing it so that we can double check. Lookup backend service. Voila. You can see that the backend service is actually got a long host name, fully qualified host name. But we can also resolve it just using backend service. And this is a reliable IP address that we can actually use. It is really cool. So the servlet running on the Jetty simply need to use backend service as a name. So we don't have to worry when we develop the service, we just really hard code this name that will later on be resolved to an IP address. So that's done. Now if we exit that and then exit from this node, we back to our Cloud Shell. So the next stage is we deploy the front end service. And now the front end service is a little bit different. The front end service is actually of type a load balancer. And load balancer is basically an external type of service, external to Kubernetes. In this case, it will be deployed as part of the Google Cloud Platform. It will be an external load balancer, and it will have an external IP address that's exposed to the internet. And the load balancer will run on port 80, and then it will forward to our containers or pods running on port 8080. on the 3 front-end pods. And if you want to see how this looks, is basically these are the green ones. These are the 3 front-end pods, and this is the front-end service, which is effectively a load balancer, and it simply provides transparent load balancing between them. And we create this controller, this service, by using the kubectl command, create -f front-end service. Bang is created. If we verify the status of all the services that we've created, now let's describe our service, our front-end service. So we use the kubectl command, describe services, and we describe our front-end service. Okay, so we've got a service here, and it's still under creation, so it still says creating load balancer, and that's because it's external to Kubernetes. It's being created by container engine. If we try again just to see that if it's created or not, brilliant. So you can see the second message here, it says is created, and we have an ingress address, which is a public IP address exposed on the internet and can be used to access basically our web app, and it should really just load balance between the front end. Now if we go back to the Cloud Console and just to double check that this service is actually created as an external load balancer, if we click on network load balancing, you can clearly see that Container Engine has successfully created for us a network load balancing. If we click on it, it shows more details. So it's listening on port 80, and this is the external IP address, and it's got a target pool. The target pool is simply our 3 instances. So if we click on that, you can see that it's load balancing between these instances. Actually, it's load balancing between them, but Kubernetes internally will forward them to, because the service is listening on there, will forward them to the relevant pods. We go back, we click on the external IP address, and that external IP address should take us to our web app. And now I can click run the graph. That should go to the front end pods, one of the front end pods, and then that will make a request to backend service, which would resolve to an IP address. Backend service, you will then request from one of the backend pods, and that will generate the graph and then send it back to us. So at this stage, we've got the cluster fully created. When a user hits the load balancer, it goes to one of the front end pods. The front end pod says, okay, I've got this text, call one of the backend pods and generate a graph that calls the service, backend service resolved to an IP address. It might be this one, it might be this one. Sends a request here that generates the graph in SVG, returns back to the front end pod, and the front end returns back the graph to the user, which is what we see in the web UI. Next step is we test the load balancing. We are now testing the load balancing of the front end service and the backend service. You might notice that the IP address is different because I recorded this on a different cluster, but it's the same principle. So the 3 consoles I've got at the top, they are for the front end containers, and the ones at the bottom for the backend containers. So if I hit run the graph, you can see that the request is being sent to the one on the right, the front end, and that's gone to the backend again, the one on the right. If I hit again, it's using the same front end. However, this time the backend service is doing the load balancing between the two backends, so it's sending it to the other backend. Now if you refresh the page and then hit run the graph, again that's gone to a different front end container, and it's gone to the backend container. And then if we do that again, you can see it's actually gone to a different one. So effectively, this demonstrates the load balancing capabilities of the Kubernetes services. We have successfully shown that we can load balance between 3 front-end pods and 2 back-end pods using 2 different services. The one on the front end is actually exposing an external load balancer. The one on the back end is just a straightforward